For the last two examples, we're going to change how we decide to define the system. In this case, for the third problem in your notes, we're going to define the system as only the cart and the earth, so we're not going to include the spring. So let's draw a dashed line around our system, and deliberately we're choosing not to include the spring. And let's just now assume for the last two problems that friction is not that significant. So in the beginning, let's look at whether there's any energy present within our system, the system being the cart and the earth. Well, the cart or the earth is not moving, so there's no kinetic energy. At this point, the car and the earth are not separated, so there's no gravitational energy stored in the Earth's gravitational field. It's at a height of 0. And the spring is in our system. That was the thing, remember, that was storing the spring potential energy. And so the car and the earth, they don't have any spring potential energy. And so in the beginning, there's no energy. There's 0 energy stored in our system. Well, let's look at the end. In our system, remember, it's the cart and the earth. The car is moving, so there's kinetic energy in our system. The car and the earth are separated. Well, the car is separated from a height of 0, so the car and the earth together have gravitational potential energy. Let's say it has 2 bars. There is no spring potential energy because there's no stretched or compressed material at this point, and there's no thermal energy because we assume that there's no heating up due to friction. So we've got a problem here now. Remember, we talked about energy conservation. We said that all the energy in the beginning has to be equal to the energy in the end. Well, we have no energy in the beginning, but we do have energy in the end. Well, that just means that there must have been some energy that entered our system. So if we have 4 bars in the end, we've got to have 4 bars coming into our system. Now, when there's an energy transfer into a system or out of a system, we call that work, or work is being done. Since there's energy entering our system, we'd say that positive work is done on the cart by the spring. Now, positive work is energy being transferred into the system. And remember, work is done when an object feels a force and it's being displaced while it feels that force. If the object is being displaced in the same direction as the force exerted, then positive work is done and energy enters the system. Well, what was doing positive work on the system? Positive work was done on the cart, which is part of our system, by the spring, because the cart moved to the right and the spring was pushing on the cart to the right, which is why it was doing positive work and adding energy to our system. Let's see how the energy conservation equation looks for this situation. So this is a situation where the total energy is not constant within the system. It's because we had energy entering our system. So the change in energy is not 0. There is a change in energy. It went from 0 to, in this case, 4 bars of energy. So when that happens, this is the energy conservation equation. It's not that it's 0. The change happens because there's work being done. Energy is either entering or leaving the system. In this case, we know that it was entering the system. So another way to write this is to show that the initial energy plus or minus the work done plus or minus the transfer of energy in or out equals the energy you get in the end, or the final energy. In our situation here, we can see that the work being done must be equal to the sum of the kinetic energy and the gravitational potential energy. In equation form, it looks like this. The initial energy plus the work done is equal to the kinetic energy and the gravitational potential energy. This is not a generic equation which holds true in any situation. Remember, this comes from looking at our system. What's true in the beginning, what's true in the end, how did we define our system? That lets us know how we can set up our energy conservation equation. For the last example, we're just going to define our system as only including the spring. So We're just going to circle the spring and only include energy before or after if the spring stores it. So the spring is our system, so let's write the word spring in our circle. In the beginning, our spring, it's not moving, so it has no kinetic energy. It's at a height of 0, so it has no gravitational potential energy. But, like we said before, the spring is the thing that stores the spring potential energy. In the end, it's relaxed, it is uncompressed, it no longer has the spring potential energy, and the spring's just sitting there at a height of 0 at rest. It hasn't rubbed against the ground. Remember, we're saying that friction is not significant, so the spring has no energy in the end. It's got a lot in the beginning, it has none in the end. So similar to our last example, we have to think about, well, was energy transferred into our system in this case, or out of our system? Well, if the spring started with energy and in the end it has none, that means energy must have left our system. So if we started with 4 bars of energy, we have to show 4 bars of energy leaving our system. Well, if energy was transferred out of our system, we're going to say that work was done. It's one of the 2 mechanisms of energy transfer. The other one is heat, but we're not going to really focus on that in this chapter. We'd say negative work is being done on the spring because energy left our system, and it was done on the spring by the cart. We'll talk a little bit more about that in just a second. So negative work means energy is transferred out of the system, and this happens if the force exerted on the system and the direction of the displacement are in opposite directions. So we need to think a little bit deeply about this. So our spring, while it's uncompressing, is moving to the right, so the spring has a positive displacement. While it's moving to the right and being displaced in the positive direction, it's feeling a force from the cart backwards to the left in the negative direction. We know this because of Newton's third law. If the spring is pushing on the cart with some amount of force, we know that the cart has to be pushing back on the spring with the same force in the opposite direction. So the spring is being displaced to the right, feeling a force back to the left, which means energy must be leaving the system and negative work is being done. Our energy conservation equation for this situation is the initial energy minus the work being done, because the energy is leaving our system, is equal to 0. So the spring potential energy that we started with minus the energy transferred out is equal to 0 in the end.